Okay, now that we've reviewed this notion of linearly independent set of vectors and thinking about spans of sets of vectors, we're ready to connect these ideas and define what might be one of the most essential definitions in linear algebra, which is a basis for a vector space. So let H denote a subspace of some vector space V. Then a set of vectors that we'll denote with this script B is a basis for this subspace H if it satisfies two properties. The first is that all of the vectors in this set B are linearly independent. The second is that this subspace that's spanned by the vectors in B equals all of the subspace H. So namely, if the span of the vectors in this set B gives us all of H, and the vectors inside B are linearly independent, then we say that this set B is a basis for subspace H. I think the best way to investigate this definition is to take a look at some examples. So let's consider this set of 5 vectors that we first considered and think about, well, is this set of 5 vectors going to be a basis for our vector space here that we're considering is going to be R3. So not even a subspace of this vector space, but our space H is going to be the entire vector space R3. And so does this set of 5 vectors form a basis for R3? We kind of seen the answer to that. Versus, well, what about this set here, these 2 vectors over here? Would this be a basis for the vector space R3? What about these 3 vectors over here? So I have 3 different proposed sets of vectors. The first set has 5 column vectors. Each of them is in R3. The second set has 2 column vectors. The third set has the 3 standard column vectors. And this first set of 5 vectors is not a basis, right? Because we've already commented that this set of 5 vectors violates the first property. It is not a linearly independent set. This vector over here, 1, 0, minus 1, can be written as a linear combination of vectors that precede it. Namely, it can be written as a linear combination of 1, 0, 0, minus the vector 0, 1, 0. And similarly, this last column vector, 0, minus 2, 5, can be written as a linear combination of 2 of the preceding vectors in this set. So this is not a basis. Secondly, if we look at the set that contains just 2 vectors, 1, 0, 0, and 0, 1, 0, this is not going to be a basis for all of R3 because it does not span all of R3, right? We cannot get any vectors in R3 that have a non-zero entry in the bottom position just by taking linear combinations of these 2 vectors. So you can see so far, this set of 5 vectors was not a basis because there's too many of them. They're a linearly dependent set. This set of 2 vectors does not form a basis because there's too little of them, where we are not able to span all of the vectors in R3. But this last set, right, this is kind of the Goldilocks here, right? This is just right over here. Picking these 3 vectors satisfies both of these properties. And it's easy for these 2 properties to get in the way of each other, right? The more vectors we add to a set, it makes sense that we would be able to span more and more vectors. However, each time we add a vector to our set, we need to make sure that we are not adding a redundant vector, which could already be written as a linear combination of the preceding vectors. So this is very much like the Goldilocks looking for the most comfortable bed, right? This one doesn't work because it's too big. This one doesn't work because it's too small, and this one right here is just the perfect amount. So this would be considered our efficient set of vectors that we need to span R3, and we call this a basis.